Yeah, what I talked last year was sort of a pleasurable talk. There was very little mathematics, some, but little, and a lot of ideas of art and slides and art pieces. This is more serious and probably more boring, but I hope it will strike I will touch your interest, because it has to do with learning, and in that sense I think that there is a number of people in the audience that may be interested about it. Now, I remember when I first started working on learning, everything I had in my mind was learning a function. I mean, in my very, very still poor view of the subject, if the function had a value 0, 1, you were dealing with a classification problem, and if the values were real numbers, arbitrary, you were dealing with regression. This is something which is slightly different. It's none of these two cases. In a way, it can be easily understood. A function is simply a relation in which given an x there is an only y. But take any binary relation in which given an x there may be many y's. Okay? Then what you obtain is not what? When you have a function from the plane on a real function, what you get is a surface. But if you have a circle, a sphere, it's not a function, because no matter how you look at it, you have two values. Okay? So imagine you want to learn that, but what exactly would that mean? So the idea is, take this. This is I think people in computer vision use this sort of data structures that are called point clouds. You have a number of points, okay? The way this is drawn, you somehow guess that we're talking about a sphere here, okay? The way this one is drawn, you get the impression that we are drawing a torus, okay? The question, when we want to talk a bit more seriously, is can we learn the shape of a manifold M, which is included in Euclidean space, from a cloud of points? Okay? Obviously, the points need to be on, or very close to, this manifold M. Okay? So the idea is I will draw randomly, as usual in learning theory, points from my manifold, and at some moment in time I will stop drawing, I will do something, and I will tell you this is a sphere, or this is a torus, or this is whatever. Okay? Of course, there is a question, the points need to be close, but how close? We will need sufficiently many points. Obviously, if I only draw 3 points on the plane, and they have 3 points, and they draw a triangle, what is this? It can be anything. I need definitely more points to tell you something. But how many? Obviously, our answer cannot be certain, No matter how many points I draw, there is always the possibility that here there are a very, very tiny circle and I didn't draw any point from this circle and they are missing this circle. So I'm just giving you a partial answer. I am not giving you the right answer. And finally, last but not least, how do we describe the shape of a manifold? What do I mean when I am talking about the shape of a manifold? Okay?
Are you also considering the case that when you have cluster points, you need some outlier points around? So you have your manifold?
Yes.
And you also have some cluster, some outliers?
No, I don't have, I don't have outliers. Let me, just to give you an idea of why this could be interesting, in which sense you are, suppose you gather information about, this is typical right now, we have huge amounts of information, and we simply try to understand what is behind this information. So for instance, we have lot of data about the people, and we know that the gender of the person, the age of the person, the nationality of that person, and then the fact that he bought this book or this music or whatever, a series of preferences. And therefore what we get is a number of variables, if you want, very, very large, that can take certain values. And we want to know, okay, in a huge population, there must be relations. These variables must obey some relation. It's not simply some homogeneous bulk of points on that space, but in general.
Assumption of the data.
Yes, you can, yeah. So this is what we try to learn. So what is this relation? And the relation, when you have a relation, the points that satisfy this relation is a subset on your space. So we are talking about geometry, and we will not talk about differential geometry in the sense that we will not try to look for equations for that, because the equations will depend on how do we choose coordinates, it will depend on many things, and probably it simply doesn't matter. But what we really want to know is the topology. Okay, so I don't know how familiar you are with algebraic topology, but this is a very good question. Are you familiar with algebraic topology? Yeah, no, a little bit. So some yes, some no. But let me tell you, there are a number of things. When you do geometry, there are a number of properties that are metric, that has to do with measuring things. Like, for instance, the curvature, how curved is a surface, for instance. But there are others that are really, really sort of very, very general. The dimension, okay? How many connected components, the number of holes it has. These sort of things you can twist and bend and stretch and your object and will not change. Curvature or distances or angles do change, but these things do not. So we are very, very general. There are exactly these features, the ones we want to learn. Okay, so let me give you an example, very simple example. I have these 8 points, okay? So one possibility is that I draw these 8 points from this curve, okay? Another possibility is I draw them from this curve. Now these two curves, in a way, are different, okay? This has 2 connected components, this has 1 connected component. This is connected, this isn't, okay? Of course, if I had more points, I would guess with more confidence, and I am using purposely a learning theory word, I would guess with more confidence that I'm talking about 2 circles. Or if you want, that I am talking of an object that has 2 connected components. Okay, a curve with 2 connected components. Okay, but with only 4 points, really these 2, or 8 points, I can't really tell much. Okay?
Can you see this as a generalization of a model fitting, I was thinking? Kind of
model fitting, which is quite popular in computer vision.
I don't know.
So you go to model some data. Like for example, in computer vision, you have an image with some points.
Yes.
Part of the circle, and you want to fit the circle.
Yes.
But the difference maybe there is that we don't have a function. So we want to learn the function.
Here you want to, yeah. Well, he doesn't want to learn the function.
No.
It's not a function. Yeah, here is like my points have only 2 variables, whatever, age and weight. And I am trying to learn whether there is a relationship with, and this relationship doesn't need to be a function, but just a relationship between, and I don't want to get a very precise function, but just very, very rough properties.
You want to guess in the structural properties.
Yeah. For instance, if instead of two variables, if I am two variables, of course it will be a curve. But if instead of two variables I have 1,000 variables, my object may have any dimension, doesn't need to have dimension 999, does not need to be a hypersurface there. So I am really trying to understand it. It may be, it's a lower dimensional object living in a higher dimensional space, and there are a number of properties I may want to know about this object. So this is one notion that was originally introduced by a mathematician called Federer, but then Smale and company rescued it, called radius of injectivity. And the idea is the following. Take M to be a smooth, compact submanifold of Euclidean space. Okay? So a circle or any of these two curves we draw before. Tau of M is the largest number tau satisfying the following. If the distance from a point X to M is smaller than tau, is a d which is smaller than tau, then there is a unique point in M at distance d from X. So for instance, take this curve, okay, and take a point here. If you're in this point, there is only one point at this small distance. Okay, if you are here, there is only one point in the curve at this distance, d.
So if you take a circle,
if you take a circle, what will be the tau of the circle? Will be its radius. Okay? Because if the distance is smaller than the radius, then there is only one point. But if the distance is exactly the radius, then you can take as point X the center of the circle, and you have infinitely many. Not more than one, infinitely many. Okay? Which is a little bit here. If I take here, this is small, is the red one. But if I take a very long distance, like the green one, a point here has 2 points at the same distance. Okay, so this tau is the smallest number, so that the minimization problem, find the closest point, has a unique optimum. There is a unique closest point. Okay? Interestingly, this number also measures how close is M of losing its character of being a smooth manifold. Let me show you with a little picture. If you look at this, which is it's close to one of our first pictures, okay? The tau here is very little, is small. Why? Because this point here in the middle, it has two closest points that are very, very near. Of course, if I am around here, this is fine. But if I am here, there are two closest points which are very, very... And indeed, I can squeeze a little bit my curve, and it's no longer a smooth manifold, because here there is a singularity. Okay? So, homology groups. This is the way that mathematicians use algebraic topologists, not mathematicians, algebraic topologists, to describe, nowadays, is the closest, the best way of describing the topology of an object. It does not completely describe the topology of an object, in the sense that there are objects that have different topology but the same homology groups, but those are weird animals. In general, if you give the homology groups of a manifold, you're almost describing the topology of the manifold. What are these homology groups? First, there are commutative groups associated to M. And I have an index L here to say that there are many. Okay? If the dimension of the object is K, then HL is 0 for all L greater than K. So there are many but finite. And how many? Essentially the dimension. To be precise, the dimension plus 1, because they start on the 0th group. The rank of the 0th one is exactly the number of connected components of the manifold. So if I have a manifold consisting of 3 little circles, the H0 will be Z to the power 3. Okay? And for L greater or equal than 1, the rank of HL, which is called the Lth Betti number, counts the number of holes of dimension L of M. What is the number of holes? This is, let me just give you, this actually is not a definition. The definition is a very formal thing that I want to spare you. I will not give you the definition. It's a course of an algebraic topology, but just an idea. And what I'm talking when I talk about holes of dimension something. Let's see. Both the sphere and the torus have a hole of dimension 2. They have a hole inside. You have an idea of inside and outside, and the inside is surrounded, is wrapped, the boundary is something of dimension 2. Okay? So no problem in this sense. The H2 of this thing is Z, the H2 of this thing is Z. What about holes of boundary dimension 1? Boundary dimension 1 means that the hole should have as boundary a curve, and a curve meaning something like a circle. How many can we find here? Well, let's start here. How many can we find here? There are 2, now I need to leave them. There are 2 which are very different, okay? One is this circle here. If you have this circle here, there is no way that you can just, imagine this circle is a string. There is no way you can pull the string out of this torus. It will be, no matter how, it will be on the torus. Okay? You see here is completely different. If I put this string here on top of the sphere, I can take a piece of the string, I can begin pulling, and the string will, on the sphere, will become smaller and smaller and smaller and smaller, and eventually will disappear. So there is no way I can draw with a string a circle on the surface of the sphere, and the circle will be relevant. All the circles are in a way irrelevant because I can pull them. So they are not really, there is no really any hole in here. I can put it, but since there is no hole, I can plug it. This one here, there is no way I can plug it. And this one, you probably will see it clear, there is no way I can plug it. Once I put it here, if I pull, the only way that I can reduce this to nothing is to remove the string from the surface of the torus. So this one has no holes of dimension 1. This one has at least 2 different holes of dimension 1. So here the group is the trivial group, 0. Here the group is Z modulo Z2, Z squared. Okay? Okay, this is the toughest slide, because if you've ever seen algebraic topology, it's slippery, okay? But just keep in mind that these groups tell me practically everything I want to know about the very, very rough properties of the manifold. So let's go to learning. Now, yes. NSW stands for Niyogi, Smale, and Weinberger. Smale is a mathematician who has done everything. Weinberger is a geometer, and Partha Niyogi was, among other things, a very, very good learning theorist. They proved the following things. They proved that, assume that you have a finite collection of points in a manifold. So we are beginning to be close to what we are interested in. We are drawing points from a manifold, but for the time being, don't think on probability, just geometry. I have a finite collection of points in a manifold, which is epsilon over 2 dense in M. This means that for every point in M, there exists X in X at a distance at most epsilon over 2. Okay? So my collection of points is sufficiently dense in M. I have points in, any point in M is sufficiently close to a point in X. Okay? Suppose that epsilon is bounded by this number, which is smaller than 1, tau of M. Remember, tau measures how close we are of not being a manifold. If this happens, then M is a deformation retract. For those of you who know topology good, if you don't know, simply forget about this expression. And what is important is that M and U epsilon have the same homology groups. And what is U epsilon? U epsilon is the union of the balls with center X and radius epsilon.
And these are non-intersecting balls, right?
No, they are. They do intersect. They do intersect.
Yeah, I got that.
They do. Yeah, they do intersect because I don't know what I have. Let me see. Let me try to find some drawing. It's something like this.
Mm-hmm.
So the idea is that I have on this manifold, the red manifold, I have plenty of points here X. I take all these balls and then I consider the union, and the union gives me some sort of enlargement of the manifold, full dimensional enlargement, because it's the dimension of this union of balls is the dimension of the union of the ambient space. Okay? And then this union and the manifold have the same homology groups. So I can, if I am in this situation, so for this epsilon small enough, my set X is dense enough, then I don't need to compute the topology of M. I have enough to compute the topology of U epsilon. Now, why this is a very good news? Because of old result in algebraic topology called the Nerve Theorem that says that to any collection of balls, we can associate a combinatorial object called simplicial complex N, such that again N and this union have the same homology groups. So the fact that I want to bring to your attention is just fact number 1. In our case, in which all balls have the same radius epsilon, we can easily compute the nerve, this combinatorial object, this simplicial complex, from the data X and epsilon, the collection of points and the radius, the common radius epsilon of all the balls. And number 2, given the nerve, the computation of the homology group is quite straightforward. Because this is...
When you talk about simplicity, or in terms of complexity of the algorithm?
In terms of... in both terms of complexity and I would say also it's algorithmically simple. I mean, you don't need to come with a extremely sophisticated algorithm. So it's easy to explain.
Yeah.
Okay.
How can you guarantee that by doing your sampling you have this epsilon alpha
You can.
assumption?
Oh, you cannot.
Okay.
Oh, no. For the time being, I am saying, yeah, very good question. It's the next slide, actually. So for the time being, the only thing I am saying is the following. If for this epsilon, which is small enough, my set X is epsilon over 2 dense in M, then I am done, because given my X and my epsilon, I can compute this, and once I compute this, I can compute the nerve, and when I compute the nerve, I can compute the homology groups of the nerve, and the homology groups of the nerve are exactly the same as the homology groups of M, because M has the same homology groups of U epsilon have the same homology groups as the nerve, and the homology groups of the nerve I can compute. It's a combinatorial thing. It's no longer, I somehow abandoned the very continuous geometry, and I am doing something called combinatorial geometry, which is easier. Now, here comes your question. As up to now, I haven't talked about learning. Okay, now yes. Let's assume that we endow M with a uniform distribution. Okay, M is a manifold, and this is compact. The fact that this compact means that it has a volume. Okay, so if you have a circle, you know what is the length of the circle, and this has a finite length. Okay, you know the radius. Given a radius, you have a length. You have a sphere. Given a radius, you have a surface, an area. And in general, you have a manifold which is compact. Of course, your manifold goes, if you have a parabola, there is no length. It goes to infinity. But if you have a compact manifold in n-dimensional space, then it has a volume. Your manifold has a dimension k, and then it has a k volume. So you can easily take a probability measure there, simply giving to any little piece, measurable piece of the manifold, its volume divided the total volume of the manifold. So the manifold will have measure 1. Okay, any measurable subset of the manifold has probability measure, its volume divided the volume of the manifold. Okay? Now, let epsilon, consider any epsilon which is smaller than this number. It depends on the quality. This is a measure of the quality of your manifold. Remember, if this is very, very small, it means that your manifold is very close to no longer being a manifold. You squeeze it a little bit, and it has a singularity. Okay? So let epsilon be smaller than 2m over 2, and let x be a set which I sampled from the manifold using the uniform distribution. Consider any delta between 0 and 1. Delta is my confidence. Okay? What do you ask me? How do you know that this is epsilon over 2 dense? Well, the theory, the proposition is the following. The probability that x is epsilon over 2 dense is greater or equal than 1 minus delta, provided my set x is large enough, provided I had sampled sufficiently many points. So if you go back to the original example I gave to you with the 8 points, the 8 definitely does not satisfy this. But when I took the second one, in which I had many, many little points on 2 circles, that it satisfies. So That's the idea. So if I sample sufficiently many points, x is greater than something, then the probability that this epsilon over 2 dense is large. So I have that with high confidence. And what are these numbers, beta 1 and beta 2? Well, here you see that, by the way, there is the log of 1 over delta. So if you want your confidence to go to 1, then you will have to sample infinitely many points, and so it's no good. But I think this is usual in learning theory, okay? And beta 1 and beta 2 are simply two constant, universal constants. Well, depends on m, but otherwise they do not depend on anything else, okay? K is the dimension of m, and so I am interested in the here b epsilon k is the
dimension of the manifold.
Is the dimension of the manifold? No, there are many things we don't know. We don't know tau either. So we don't know tau. We don't know the dimension of the manifold. We don't know a number of things. So ultimately, it's a matter. There are no guarantees of anything. So the theorem, like many theorems in learning theory, simply tells you that yes, under certain conditions you're learning with high confidence and blah blah blah, but then you don't know necessarily. It's like typically you're learning.
There are ways for estimating the case. There are ways for estimating the case of the dimensionality of the manifold.
Yes, in a way, yes, because if you get many assume that I sample on the plane, and then I look around the one point, and I get something that are many points on a little curve like this. Many on a little curve. I guess this is a curve. I can, why? Because transversal to one point, I get nothing. Wherever, in the case that this would be a piece of the plane, that's a dimension 2, I should be able to take a point, take many directions, and get many points which are close in several directions, which is not the case if it's a piece of curve. But this is just a way of sort of estimating. By the way, once I compute the homology, one of the things that come by as a subproduct is the dimension, because the largest k such that hk is different from 0, from the trivial group, is the dimension of the manifold. Okay. After that, I get all the homology groups being 0. But no, a priori I don't have it. You can, in terms of, it reminds me of the situation in learning theory that there are many theorems that says, okay, you're doing regression, okay? And then if your target function has a certain degree of smoothness, like say C18, 18 times continuously differentiable, then your rate of convergence is such and such. How do you know that it has 18, is C18? Well, you don't know it. But it's telling you that the smoother is your function, the better your regression algorithms will work. Here is similar. So you don't know this tau, for instance, but the larger is this tau, the better your algorithm will work.
Can I ask you about this tau?
Yeah.
Is there any connection between, I don't know if you are familiar with catastrophe theory?
I am not, well, I know of course what catastrophe theory is, René Thom, and it's a classification of singularities, I know that,
yeah,
but no, I don't know whether it has any any relation. No,
if I remember, you use catastrophe theory or scale space to find similarities as you, for example, if you're seeing something from far away,
yeah,
something that's happened in your curve, so maybe it's break or it's break.
I would not.
And then it's value.
So I would not be surprised if you have a connection.
Okay.
Because this is a very, very general thing. But this is for manifolds, and catastrophe theory in general is for functions.
Yeah.
So,
for studying curvature of
yeah,
objects, etc.
but functions are special cases. So yeah, there may be some. It definitely has a relationship with curvature. It has to do with the second fundamental form. That it's proved in Smail's paper. So the theorem of Niyogi, Smail, and Weinberger says the following. Let X be a set of n points sampled from the manifold, 0, epsilon, a number between 0 and tau over 2, and delta, a confidence. If n is greater or equal than this amount, then with confidence at least 1 minus delta, the homology groups of U epsilon, that is the union of the balls of radius epsilon, blah, 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 are equal to those of n. And are easily computable. Well, easily, okay, are computable. Okay, so this is their theorem. And this is a very learning theory spirit. Let me go to a second case. I mean, you can say, okay, but in general, when you sample, very often there are measurement errors. There is some noise, okay? So Smail and collaborators say, okay, yes, let's take as a model that the support of the probability measure is contained on a tube of radius r around m. So I mean the following. Imagine that your manifold is a circumference, okay? Then instead of sampling from the circumference, you sample from a little crown of width r. Okay? So in an old picture, let me recover this picture here. If my manifold is the blue thing, let's assume that I am sampling from the red tube that has radius r. Okay. We also assume in the model that for every s smaller than r, the infimum over the manifold, this is not an assumption, it's just defined this way, I take the points in the manifold, I take the balls of radius s centered at those points p, and I take the measure of these balls, and this is greater than ks. This is simply a more general model than simply say I take uniform measure on this crown. It's a little bit more, it's more general. But the only thing, but I need to request something from the measure. I request this, that the balls cannot have a measure which is too little. Okay, if my balls have radius s, they need to be larger than, no matter where they are centered, they need to be in measure larger than a certain constant, k sub s. Okay? And then n sub r is the smallest number of balls of radius r needed to cover m. M is compact, so definitely I can cover it with a finite number of balls, because from any infinite covering I can take a finite covering, and then I take some sort of optimal. Okay? So the second theorem of Niyogi, Smail, and Weinberger says that if you have n points sampled from mu, and you have an r which is bounded by, again, this is a little bit bigger, this is smaller than 1. Again, so it's smaller than tau, again, bigger than 1/2 or something like that. And then this is the important thing: if epsilon belongs to this interval, just to give you an idea, if you take tau, r equals tau divided by 6, epsilon should be between 3 and 4 tau. Okay, but of course they gave this very general version. And again, you take a confidence. Then if n is greater than 1 divided kr over 2. Remember, kr is the smallest measure of balls of radius r. Log nr over 2. Remember, nr is the smallest possible covering. Log 1 over delta. Well, delta is my confidence. Then, with confidence at least 1 minus delta, the homology groups of u epsilon are equal to those of m.
So this generalizes the previous.
So this.
So when the noise, there is no noise, you get back to the original form.
Exactly. So it generalizes in 2 senses. First, if there is no noise, you are back to the. Second is a little bit more general, because in the first version you are somehow taking the uniform measure. And here I don't request that it will be the uniform measure on the crown, on the tube. I simply say, okay, it can be any measure that is supported on the tube. So outside the tube, measure 0. And I put this technical condition, then say, give me a lower bounce on the balls. So don't allow that at some moment on my tube it goes to 0, the measure. I mean, if you give me a balls of radius 1/4, then there must be a number so that all balls of radius 1/4 centered at the manifold have measure at least such and such. So in this sense, this is the most general version. Now, interestingly, in the middle, in order to prove that general version, there was this proposition, which is a purely geometric proposition, and that's what caught my attention. Okay, so now I abandon a little bit. This is a transition. I abandon learning theory and I try to talk about something I am interested on. Okay. Suppose you have a finite collection of points in Euclidean space and you have an R such that X is R dense in this manifold, and 6R is smaller than tau of M. Okay? So it's what I said before. And take epsilon 3.5R. I remember I said between 3 and 4. Okay, I take 3.5. Okay? And U epsilon being the union of the balls. Then M is a deformation retract of U epsilon. If you don't know what deformation retract is, forget about it. The important thing is that these sets are homotopically equivalent, meaning they have the same homology groups. So when I saw this, I said, well, this is the picture. That could be interesting to use in an algorithm in which I'm not doing learning. I am given data and I want to learn the homology of some sort of set. So let me go maybe a bit quick over it. Complexity theory. That's what I've done. So it studies the cost to solve problems algorithmically. So what we need is we try to give upper and lower bounds on a problem's complexity. Say we cannot solve with less than this amount of operations. This is lower bound, and we can do it with this amount of operation because this algorithm does it within this cost. This is an upper bound. On an abstract level, we cluster problems in complexity classes by fixing a cost resource and a family of bounds. You must have heard about P versus NP, okay? You must have heard because there is $1 million to the person who solved it, and eternal glory and all that. It has to do with that.
My students to capture their attention. This is what I say to my students: capture their attention.
Yeah.
$1 million to win.
Yes, exactly. But it's
they will just wake up.
yeah, but it's very it's tricky.
Just places they are different.
So let me give you some examples. P, problems decidable in polynomial time. There is an idea of a size of my data. It's not the same to decide whether 47 is prime and to decide whether a number with 47 digits is prime. The second, we won't be able to do it. So there is an idea of size. In this case, we count the number of digits. And the polynomial means polynomial in the size of my data, okay? EXP, exponential, problems decidable in exponential time. Instead of a polynomial, I allow an exponentially large, so I should be able to do a number of things here. NP, problems decidable in non-deterministic polynomial time. This is not a physical notion, it's a theoretical notion. And NP is between this one. It is well known that P is included in NP and then NP is included in EXP, but none of these inclusions, none of the two, is known to be strict. One of them must be strict because P is strictly included in X, but we don't know which one. Probably those. Average P, problems decided in average polynomial time. This is interesting because now if we are on our space of data, we need to have a probability measure, okay, to talk about average. Sharp P, problem solving counting polynomial time. This has to do with counting problems, with that you can. It's again a theoretical notion. It has to do with counting the number of solutions of certain problems. The ultimate goal, but that's some sort of dream, is to classify all computational problems by locating them in this landscape of complexity classes. And this is not the landscape. This is just a few examples. There are some transparencies that you can look in the web that have the landscape, and this is something completely huge. It's wild, the number of complexity classes that people doing these sort of things have been creating. Okay? There exists this notion of a problem which is complete in a class. Those are representative problems. They are the most difficult problems within this class. And they are the most difficult in a very precise sense if I manage to get an improvement for a complete problem. The same improvement will hold for all problems in the class. In this sense, they are the most difficult. Okay, roughly speaking, whatever we can say of the complexity of such a problem can be said of the whole class. A remark, not all complexity classes have this crust, this layer of hardest problems, okay? Now, computations broadly divide into two kinds. Discrete, example, combinatorial or Diophantine problems, factorization of integer numbers and things like that, and continuous, whatever we were talking in the last transparencies. I mean, those are continuous problems. We assume that we can work with real numbers. Actually, they are floating point numbers, but in our minds, they are like real numbers, okay? And accordingly, there are two streams in complexity theory, and the continuous stream was pioneered by Lenore Bloom, Mike Shoup, Steve Smale in 1989, and is usually referred as BSS setting or complexity over the reals. Now, this is the first thing okay. Most complete problems in the BSS setting deal with polynomial systems. We have polynomials, F1, Fm, and we have either systems of equalities, like this one, you know, F1 equals 0, Fm equals 0. This defines a set, which they are called algebraic sets, the heart of algebraic geometry. Or more generally, which these are definitely more complicated, I allow for equalities and inequalities. These are called semi-algebraic sets. Okay? let me give you some examples, some basic problems. For instance, let S be a set given by a polynomial system, algebraic or semi-algebraic. Just to give you a few examples of the problems that people do find. Membership. I give you an X and I ask you, does X belong to S? Answer yes or no. Feasibility. I am giving you the set S by its description. Is S non-empty? Does there exist an X such that X belongs to S? It could be empty. I mean, I could tell you x squared plus 1 equals 0. There is no X. What is the dimension of S? It's a geometric property. What is the cardinality of S? What is the Euler characteristic of S? This is you probably read about something like that, about this, that in a polyhedron you have vertices plus faces minus edges equals 2. This thing, vertices plus faces minus edges, this is called the Euler characteristic. It's a very, very important invariant in algebraic topology. What are the homology groups of S? That's what we were talking about a few minutes ago. Well, this is in P. Very easy. You just plug the X into the equations and you see whether it satisfies the equations or doesn't satisfy the equations. This is an NP. It's more delicate. It's more difficult. How do I know when something is empty or is not empty? This is also in NP, interestingly, because it looks more difficult, and yet the level of difficulty is exactly the same. This is in sharp P, and it's about counting problems. It's more difficult. This is also in sharp P. It doesn't look like, but it is in sharp P. And finally, this one, we don't know. Actually, all these 5 things, they are complete. So not only I know that they are in these classes, I know that they are the hardest problems in these classes. Okay? They are. It's well known. But this one, I know nothing about it. So what do I know? There is a very old theorem that says that we can compute all the homology groups of S in this time. S, remember, is the number of polynomials. V is the degree of these polynomials, a bound on the degree. So I look, if I have 10 polynomials, I look at the degrees, I take the largest one. And then it's SD to the 2 to the order of n. This is not even exponential, this is double exponential. Okay, SD to the n would be exponential. SD to the 2 to the n is double exponential. So this means that computing homology groups is awfully expensive, awfully expensive. What is worse, it will always be like that, no matter which are the coefficients of your, it doesn't really depend on the coefficients of your polynomial. This worst case is not really a really worst case, it's generic. Almost always you get exactly, almost always, with probability 1, you get exactly this complexity. Terrible, terrible. Can we do better? Can we do better? What it was known up to now, Shaugata Basu and some collaborators gave a single exponential time for the last few and the first 2 Betti numbers. But in the middle, nothing. Not much more. That's it. That's what is known. In 2016, these 2 guys, Dennis Amelungsen and Martin Lotz, introduced a notion of something called weak complexity. And to understand it, we simply endow the space of data with the standard Gaussian measure. Okay, normal 0, 1, independent in all coordinates. Okay? So we talk about weak cost T when for all n natural number there exists an exceptional set E sub n included in R to the n. That's the outliers that you mentioned. Let's call them the black swans. Okay? An exceptional set of black swans such that the measure of this exceptional set is really, really small. It's 2 to the minus n. Okay, remember n is the dimension of the space. So when the dimension of the space grows, the measure of the exceptional set decreases exponentially fast. And second, restricted to data out of this set of outliers, we solve the problem with cost Tn. The motivating example is the following. Do you know what is the power method for computing eigenpairs? Okay, it's a very, very simple method for computing eigenpairs, pairs of eigenvalue, eigenvector of a matrix, square matrix. Okay. If you talk with practitioners, they tell you this works very, very good. It works, it's fast, it's reliable, it works. If you talk with theoreticians, they tell you, in 1988, Kostland proved that the expectation of the running time is infinite. In principle, I will do an infinite number of iterations. Okay? It's the expectation. The expectation. And yet it works perfectly well in practice.
Like the simplex method?
No, it's much worse because the simplex method is just exponential No, the simplex method is exponential in the worst case.
Yeah, but in practice it's very fast.
But because in expectation is polynomial, it's almost linear. That was proved by Borchardt in 1980. No, this is much, much worse. It's something like, the point is you are computing an expectation of that's something that decays like the harmonic series. So when you do the sum of the harmonic series, you get infinite, but everything is finite there. Right? So what Amelungsen and Lotz shown is that actually what happens is that there is a very, very small set of outliers that has exponentially small measure, and the measure goes to 0 exponentially fast when you increase the dimension of your matrices.
To compute this expectation, are you using a uniform distribution on a matrix space?
Yeah, a Gaussian. You take every entry of your matrix is a every entry are independent entries, and every one is a normal 0, 1. Well, it's not what I'm saying is correct because it's true, but it's true in the general case. But they are talking about Hermitian matrix, so they are complex. So you need to take, and there is Hermitian, meaning that there is some symmetry there, but it's something called the Gaussian ensemble or something like that. It's the equivalent of the Gaussian matrix.
Maybe practitioners are happy because in the real world we don't have that kind of probability distribution. The probability we have in the real world is different from one.
Yeah, but here that's correct. But here, no. But what they showed is that in that measure, on that set of matrices, you remove an extremely small set of outliers, and you take your expectation conditioned to be out of this set of outliers. And then all of a sudden, the expectation of the number of iteration, which was infinite, becomes n squared. The dimension of your matrix are n by n, the dimension of your matrix. Easy. All of a sudden, it goes from infinity to linear in the size. So it's extremely, it was simply a tiny set of outliers that were just bothering you. Okay?
Can you just use the same approach? You know, for example, let's take the graph isomorphism problem. So far, we don't know whether it's NP, is NP complete, but again, in the vast majority of cases, we have very good algorithms that there are very tiny class of graphs. It's called double regular graphs, where it's really difficult to solve the problem. So can we use this notion maybe to kind of characterize the average complexity?
That's an extremely good question. Very, very good. Because I think there is a niche for research there. Many people in discrete computations have realized that of all the jungle of NP-complete problems, some of them in practice are untouchable, and some others, well, you manage to do things. So they try to give explanations of many different kinds. And the kind of explanation that I know it worked, the sort of approaches to deal with NP completeness. Average complete, average complexity. Say, okay, worst case is exponential. But yeah, exactly. But on the average, it works fine. Another example that I know is something called parameterized complexity. And they have dealt with the graph isomorphism problem. I can check for you, or I can ask. I know the right person to ask. Some American living in Norway, in Bergen, Mike Fellows. That's his name, Michael Fellows. They got the Gödel Prize for this parameterized complexity. And then there is a third approach, which is for problems that have an optimization nature, to find approximate solutions instead of near optimal. 1 minus epsilon multiplicative factor of the optimal solution. For the decisional problems, the computational problems associated with the decisional problem, which is NP complete. But as far as I know, because this is extremely new, nobody has done this for discrete problems. All the examples that Amelunxen and Lotz have dealt with are in continuous complexity. But I have talked with them, and they told me, because I said the same question, they said, yeah, this holds well for discrete complexity. You have the same idea.
Yeah,
and it's different from the idea of average complexity, because in average complexity you compute an expectation. And you can have an expectation, let me put it that way. How can I give an example? I remember I had to explain this to a friend, and so the whole problem is that when you integrate something that decays, the tail decays like 1 over t, for a non-negative random variable, the expectation can be characterized as the integral of the tail. The expectation of x is the integral between 0 and infinity of the probability that x is greater or equal than t dt. So you integrate over t between 0 and infinity, you integrate the tail, and this is the expectation. Okay, this is a classical result and extremely useful. If your tail is decaying as 1 over t, you're integrating the harmonic is infinity. The integral of 1 over t is infinity. Because it's a logarithm at infinity, this is infinity. And yet, the fact that it's decreasing as 1 over t, if you remove just the tiny end and you integrate up to something which is finite, instead of integrating between 0 and infinity, you integrate between 0 and a million, and you get log of a million, which is not that much. Which is not that much. So, the idea is that even in cases in which average complexity does not help, because the expectation is large, you can still say, okay, what I will do is instead of considering all the data and get an expectation, I will just kick out some outliers and then focus on the remaining part. And on the remaining part, I can consider what they did, weak average complexity. So they consider an expectation conditioned to be out of the exceptional set. Or you can do what we did, which is a worst case complexity, but out of this exceptional set. And this is what we did. We're now computing the homology of semi-algebraic sets. We consider semi-algebraic sets, this sort. M, of course, is smaller or equal than n. N is a number of variables. So if we have more polynomials than variables, then we don't intersect anything, it's empty. We have this S can be as many as you want, And then we consider P sub D MS, the space of all polynomial systems of this sort. So I fix the D, I fix the degrees of the polynomials, and I simply say once I fix the degrees of the polynomials, this is a linear space in which I can vary the coefficients. For example, polynomials in one variable, degree 3, they have 3 coefficients. Degree 2, they have 3 coefficients, ax squared plus bx plus c, so abc. So the space of coefficients is all 3. If I have many polynomials of different degrees in different numbers of variables, I get one linear space of all the polynomial systems with this number of polynomials, m plus s, and this pattern of degrees. I can call D the maximum of the degrees, and I can call N the dimension of this linear space, which is the size of my inputs. Because in order to give an input, I need to specify the coefficients. Okay? And I call SFG the solution set, which is a semi-algebraic set. So the theorem to be, it's not completely written, but almost. And is that there is an algorithm that given the pair FG, the equalities and the inequalities, returns the homology groups. Betty numbers and torsion coefficients is the same as saying homology groups of this semi-algebraic sets with the following properties. With probability at least 1 minus SND to the minus n. So I remove an exceptional set. I remove an exceptional set of measure SND to the minus n. We have that the cost of my algorithm is singly exponential. SND to the order of n cubed, constant times n cubed. So it's not SND to the 2 to the n. The exponent is not 2 to the n, but is polynomial, n cubed. So it's exponential time. One could be happy with this statement only, but one needs to realize that if n remains fixed, and d grows, assume that I am working on the plane, for instance. So I am working with semi-algebraic sets on the plane. If I'm working on the plane, n is 2. Okay, and then what grows is s and d. And then this statement here is not weak complexity, because this set here is not exponentially small. It's polynomially small, because this is minus 2. Right, I am saying I take s and t to the square, and I take the inverse. This is polynomially small, not exponentially small. Okay, and then we add the following. So we consider now this n, which is the data size, and with probability at least 1 minus 2 to the minus n, we have that the cost is bounded by 2 to the order of n. So this is cool. This is exactly a weak complexity statement. So we can say the complexity of computing the homology groups of semi-algebraic sets is weak exponential. Okay, and this is an enormous, we are happy with that, an enormous advance over the doubly exponential that existed before. This notion of weak came in the good time, because otherwise, to get this without the probability statement, we don't know how to do it, but with the probability, yes, it's cool, it's simple, and that's all.
Thank you very much.